So, we will talk about mainly two concepts before we wind up the discussion on the fractional quantum Hall effect and as well the course on quantum Hall effects. So, this the first one of them is the composite fermions. And this was introduced by J.K. Jain. Okay. So, this is an alternative approach to understand the fractional quantum Hall effect, and particularly to understand the even denominator fractions that are observed experimentally, whereas the Laughlin states are valid for the odd denominators, which are of the form of 1 over m, where m being an odd integer. So, particularly the fractional feeling of nu equal to half was to be explained, which is one of the simplest fractions, but of course, this cannot be explained with the concept of the Laughlin wave function, the Laughlin states, which are for odd denominator. All right. So, this picture, the composite fermion, which we will call as CF as abbreviation. So, this is an effective picture. It comprises of quasiparticles, which are the electrons. They are carrying even number of flux quantum. So, they absorb the flux quantum from the external field, and so they sort of are considered as quasiparticles, and these composite fermions drastically reduces the complexity of the problem, and one actually gets starting from a very sort of strongly interacting fermionic system, which is the nature of the quantum Hall fluid. We get a picture of non-interacting fermions. And so, this was a very nice idea, and not only it's an idea, but it also has the implications have relevance on the experiments such as the Shubnikov-de Haas oscillations, and they also verified in thermopower experiments and so on. So, they are of course ideas, and in reality they are the electrons do not sort of absorb these even number of flux quantum, but it is a picture that aids us in understanding the fractional quantum Hall effect. Okay. So, let us try to visualize this. So, what happens is that, so these are I am drawing an electron to be really large, and this is carrying 2 flux quantum. So, so let us call this as 2 CF, and here they are 4 flux quantum. So, let us call this as 4 CF, and then there are say even larger number of flux quantum, which are say the 6 of them. So, this let us call it as 6 CF. Okay. As if it is a bound state of an electron, and even number of flux quanta. So, that is the intuitive picture. As I told you that it is not a real picture, it really does not happen that these fermions actually absorb even number of flux quantum, but suppose we assume that these are the this is the situation in sort of for the fractional quantum fluid, that these fermions have absorbed, or they are really carrying this even number of flux quantum, then of course the picture changes intuitively, and it gives rise to something that is quite interesting. And as I said, that it has a relevance, or rather it conforms to the experiments that are made, or rather they are performed, and these picture supports those experiments. Okay. So two sort of artifacts happen. So it's experiments. There are others as well, but I have not written them, such as thermopower, SDH oscillations. We have discussed this in our earlier lectures, Shubnikov-Dehaas oscillations, etc. are supported by these CF picture. Number 2, so it of course explains the fractional feeling of the Landau levels, and basically their connection to FQHE. And third, and probably the most important thing which I just said is, let me write it in the next page, 3, and this is quite important. So this says that the strongly interacting electrons absorbing most of the flux quanta rather, become weakly interacting electrons in a weak magnetic field. And this tells you that the latter corresponds to the integer quantum Hall effect, which we have seen. So this picture of FQHE, this goes over to IQHE. So this is for fermions, IQHE for composite fermions. Okay. So this is a big simplification that occurs. Okay. So let us see what happens and how it happens and so on. Okay. So we just said that the electrons actually absorb the flux quanta. So the effective field is reduced. So let's write down the effective field. Which we'll call it as B star, which is actually reduced in the CF picture, is given by, so B star is equal to B, which is an external field, and then there are these even number of flux quantum, which we write as 2p, and then each one carrying a flux phi and the density of the composite fermions. So B star, of course that is written, so let me write B, which is the external magnetic field, okay, 2p even number of flux quantum, phi 0, of course you know that that's a flux quantum which is equal to H over E, and rho density of CF. So this tells you that the magnetic field, the effective magnetic field or the reduced magnetic field is given by this expression, which is this B is the external field, and now since these fermions have absorbed most of the flux, from the external field. So, the field now remains as this, and let us now see that what this means in terms of the electron filling. So, the filling fraction for the CF, let us call that as nu star in keeping with a B star, which is equal to rho phi 0 divided by B star. Okay. And this is of course understood that the B is pointing in the Z direction. So, we should also mention that here. So, B is in this direction, the external field is in this direction, and let us call this as equation 1 and this as say equation 2. That is the definition of filling fraction, which is rho, that is the density of the fermions, composite fermions multiplied by phi 0 divided by the B star. So, putting 1 in 2, what I mean is put this B star B minus 2p phi 0 rho in 2, one gets a nu star to be equal to rho phi 0 divided by B minus 2 pi phi 0 into rho. Okay. So, I write phi 0 as h over E, and this is E, and this B minus 2p phi 0 rho. Now, what I do is I take this rho also down and then sort of rho he to be down. So, this is like a 1 divided by E over rho h and a B minus 2p phi 0 rho, and then a little bit of algebra. So, I take this in. So, it is E B by rho h and a minus 2p phi 0 rho into E by rho h. So, rho will cancel and E by h is 1 over phi 0. So, that will cancel as well, and we are left with E B over rho h, which is nothing but the filling fraction of the original fermions. Okay. So, this is the inverse of it rather. So, it is 1 over nu minus 2p and so on. So, this is the thing, and so let us call this as equation 3, and then we can write down the nu star in terms of this nu to be equal to nu minus 1 minus 2p nu, and let us call this as equation 4. So, this is the expression for the filling of the composite fermions and its relation to the filling of the actual fermions which are there in the system, and this p is equal to 1, 2, 3, and 2p denotes the number of vortices or the number of flux quantum, which are actually vortices. I will just come to that. Okay. So, it can be actually inverted. So, 1 over nu star, this is equal to a plus minus. So, this is equal to 1 over nu minus 2p, and so this is the the filling fraction relationship between the filling fraction. And just take a note that we have written both plus and minus signs, and they would give rise to new different fractions. So, to say both signs are actually allowed. So, plus and minus signs are allowed depending on whether B star is in the direction of B or opposite to it. Okay. So, this is, let us call it as 5. It is same, 4 and 5 are same, it is just written in a different language, and this can again be written in another language in which you can see that. So, if you write down the nu in terms of nu star, then it becomes equal to a 2p nu star plus 1, and this is the equivalent expression where nu is the filling of the original problem of the Hall conductance or Hall resistance. And for nu less than 1, which is what we are talking about, fractional filling, nu star is greater than 1. Okay. And when the nu star becomes large, it corresponds to the, or rather it is an integer, okay, it is equal to 1 or greater than 1 and becomes an integer, then it corresponds to the non-degenerate state, and the non-degenerate state of course would correspond to weak interaction or no interaction at all, which means that we go to the case of IQHE. Okay. So, let me make this a little more clear, because so the filling factor is defined in the following way. It is also called as filling fraction. So, this is equal to a rho divided by a degeneracy. Okay. So, now if rho, that is the density of electrons, fermions, that becomes equal to the degeneracy, which means that the integer number of Landau levels are filled, and if it becomes 2, say the rho is twice of the degeneracy, which means 2 Landau levels are completely filled, and this situation would correspond to exactly what we have studied in the context of IQHE, that is integer quantum Hall effect, and the system corresponds to non-degenerate states and or non-degenerate scenario, and that sort of should explain the non-interacting electrons or very weakly interacting electrons, which we have studied in the context of IQHE. Okay. So, this is the picture that emerges out of this composite fermion picture, and let us try to understand what is its relation to the Laughlin state. This is quite a nice explanation, so follow me carefully. So, remember the Jastrow factor, and the Jastrow factor actually says that so there is a Zi minus Zj. I might have written Zj and Zk, these are just indices which you can take according to your convenience. So, there is this m, and then of course, it is multiplied by the Gaussian. Let us look at the Jastrow factor only. You would sort of recognize that for each electron, so z's are the coordinates of the zi denote the coordinate of these electrons, and this is basically enforces the antisymmetric property by when m is an odd integer, and it also says that if Zi becomes equal to Zj, this is not only 0, but it is 0 m times because of the product that is involved here. I hope this notation is clear. We write a summation by this and we write a product by this. So, this is a sum and this is a product. Okay. So, this product of all I is less than j, and then it is a 0 of mth order, and that is what comes out from the Jastrow factor, and that is what is embedded in the Laughlin state. Now, of course, we need 1 0 of those m zeros, and 1 0 we need because of we want to enforce the exclusion principle. What happens to the m minus 1 zeros? Okay. So, these m minus 1 zeros account for what are known as vortices. So, let me write as 1 0 ensures Pauli's exclusion principle. The rest m minus 1 zeros sort of account for the vortices. And what are the vortices, or what's a vortex? A vortex is actually sort of a topological excitation. So, suppose a complex number z equal to r e to the power I theta. All of you are familiar with this polar representation. It has a vortex at the origin. Okay. So, which means that if a particle sort of encircles this origin, it picks up a phase 2 pi, so that theta actually changes from theta to theta plus 2 pi, and the complex number remains unchanged in the sense that because you have a 2 pi I, exponential 2 pi I is equal to 1. Okay. So, that is the meaning, and suppose these the FQHE wave function contains a factor z minus z0 to the power 2p. Okay, we are writing m as 2p in the sense that these are just to make p to be any integer, not only odd integer. So, 2p will be p could be any integer, so that 2p is even. 2p is an even integer. So, you see here you have this m minus 1 is an even integer, because m is an odd integer. So, m minus 1 is an even integer, and so we write that as 2p. So, this means that a fermion 1 sees fermion 2 to carry 2p vortices or m minus 1 vortices. Okay. And so, basically this means that even number of vortices, which is what this composite fermion picture it sort of proposes. So, let me tabulate a few p and nu. P and nu with nu star to be an integer, and I told you that this corresponds to the IQHE when nu star becomes an integer. So, this is a p and a nu which is equal to a nu star and which is equal to a 2p nu star plus 1, the formula that we have written earlier, and let me just show it for p equal to 1. So, this gives rise to 1/3, 2/5 and 3/7 and so on, okay, for nu star to be an integer, and for p equal to this, p equal to 1 here, let us say p equal to minus 1, we get other integers which are 2/3, 3/5 and 5/7 and so on, and so 2 will give rise to 1 by 5 and 2 by 9, and minus 2 will give rise to 2 by 7 and 3 by 11. So, you see all these fractions have been seen in experiments, they have been realized in experiments, and that is why just having nu star to be integer values with p to be plus minus 1, plus minus 2, you can extend it to plus minus 3, etc. We are getting all kinds of fractions which were not realized in the Laughlin wave function. I mean with the Laughlin wave function, which is only valid for 1 over m. is fraction 1 over m, where m is a odd integer. So, of course, 1 by 3 is in that form, but none of these other 1 by 5 is also of that form, but none other are included in the Laughlin wave function, and these are called the non-Laughlin states. So, let me show you a picture, an intuitive picture of this whole thing. So, we will draw. So, this is 1, 2, 3, 4. So, we will have this usual fermions, and then the composite fermion picture, and sort of their filling fractions will be compared. So, these are these fermions which are carrying these vortices of the flux quantum, and this corresponds to the original picture of fermions. This is like this, 4 of them in each of the 3 Landau levels, and this corresponds to a filling fraction to be nu equal to 3 by 7. Okay. So, this is a fractional quantum Hall effect, and when we go to the non-interacting picture or the picture of so this okay. So, this corresponds to nu star equal to 3. Okay. So, this is the, it is a schematic plot. This shows IQHE with filling factor equal to 3, and this corresponds to the FQHE with filling factor equal to 3 by 7. Okay. So, this is the problem of FQHE becomes a problem of IQHE of the composite fermions. Okay. And let us do the last thing in this regard. We still are missing a number of fractions. Okay. Even though we have been able to go beyond the Laughlin picture and get a lot of other fractions from this composite fermions, but we still are have not got all the fractions that are experimentally observed. Okay. And there is a hierarchy picture which again is very subtle. The idea is very subtle, though getting a lot of other fractions are not too difficult. So, this sort of relies on the fact that there are other filling fractions that are observed in experiments. Starting from some parent states, one can get Laughlin like daughter states. Okay. So, from a given parent state, so these are Laughlin like daughter states. Okay. So, these Laughlin like daughter states and a parent states which are very interesting here, and these fractions at any level, another important thing, the fractions at any level in this hierarchy scheme scheme are denoted as continued fractions. You might have seen this continued fractions even in school. The fractions carry on, and here we'll have these different at a given level of the parent state, will have a multiple daughter state emerging out, and will give a large number of these fractions coming out and so on. It's not that all the fractions are seen in experiments which are predicted from this hierarchy scheme, but quite a few of them have been observed. Okay, and it's not that, you know, at a given sort of Laughlin the daughter states, at a given sort of hierarchy of the daughter states, there could be many fractions, and the probability to observe these fractions in actual experiments, it seems to be the same, whereas some of them are just not observed at all. Some of them are of course observed. That tells you that this of course doesn't distinguish between one fraction at a given level from another fraction. Now, physical picture is necessary, and the physical picture really relies upon not the ground state which we have been talking about so far, but it relies on the excited state. And so you have a problem of, you say, a quantum mechanical problem, and you have a Hamiltonian, and you may be able to solve that Hamiltonian exactly, or maybe there are, you know, mathematical difficulties, or there are computational difficulties and so on, but it's very easy to understand that these quantum mechanical Hamiltonian will have a large number of states possible, which are energy states. There could be degeneracies and so on, but forgetting the degeneracies for the moment, there are ground state, there are first excited state, and there are second excited states and so on. Rarely ever one needs to go very far away from the ground state in condensed matter physics, because we always talk about low-lying excitations, which are the most important thing. I mean, something that's far away from the ground state may not be taking part in either the thermodynamic or the transport properties at all. So it's quite important that, and we are sort of, you know, understanding that the Fermi level lies very close to the ground state. Okay, and that's why the ground state is the most important thing. However, in certain scenarios, you may have to go beyond the ground state and take into account excitations, and these excitations in this fractional quantum Hall fluid are called as quasi-particles and quasi-holes, depending upon the shortage of density or the excess of density. So, if you have excess of density, you have particle-like excitations, which are like quasi-particle excitations, and if you have deficit, then of course you have hole-like or the quasi-hole-like excitations. Okay, so Halperin wrote down, so conjectured that these excited states have a form, okay, which are given by the psi of z. This is a p of zk, which is our usual Jastrow factor, I mean zk minus zj, product of that, and so on and so forth. And then there is a q, which is again a function of zk, and the ubiquitous these Gaussian, that would of course be there. Okay, we are familiar with this. This is a Jastrow factor, and this accounts for quasi-particle and quasi-hole excitations. And what did he propose for these QZK? So, the QZK he proposed to have a form which is equal to It's again a product of j less than k, and then it just goes all the way up to m, and it's a zj minus a zk whole to the power plus minus 1 over m. Okay. We will not go into the details. That was the ansatz that was made by him, and of course the p zk, that's the Jastrow factor, of course has this form j less than k to the power m. It's a zj minus zk to the power 2p. Okay. So, if you combine them, then psi of z, so this is the excitation above the Laughlin state, and the excitation has been included by this qzk term, which of course talks about either particle or whole, the excitations of the system. So, at the middle of the plateau, a quantum Hall plateau, the density is uniform. Okay. And so, there are number of states that are pinned to a defect or an impurity. Now, as the magnetic field is ramped up, it is increased beyond a certain value of the magnetic field, these fields or these states actually break away from the impurity, and they would cause a density imbalance. So, if the density becomes larger, we have a quasi-particle excitation, and if the density falls below, then it becomes a deficit, it becomes a quasi-hole excitation. Okay. So, this is the idea of this. So, total psi of z becomes the product, it is j less than k, and of course, it goes to m, and then it is a zj minus a zk whole to the power 2p plus minus m 1 over m, and then of course, that Gaussian thing will of course be there. So, it is zj square divided by 4 lb square. Okay. So, that is the form of the wave function, the excited state wave function. M is still an odd integer, which is what Laughlin had said. Now, of course, you can understand that this gives you instead of just m, this gives you the total j max. So, j max, the magnitude of that, it becomes equal to 2p plus minus 1 over m, and I will have to multiply it by n because there are n electrons. Okay. And I am just talking about the magnitude. So, this is n electrons and 2p plus minus 1 over m. So, this filling fraction corresponding to this scenario can be obtained if we note that the area of the quantum Hall fluid is given by A equal to so n, then it is 2p plus minus 1 over m, which is that j, and then we multiply it by the pi into 2m and lb square. Okay. So, that is the area, and the number of states within an area A is given by n curly n. Okay. So, n is equal to a B A over phi 0, where A is given by this, which I just wrote. So, this is equal to phi over phi 0, this is equal to 2p plus minus 1 over m and m square n. Okay. So, that is the number of states that you obtain, and when we get the number of states, the filling fraction is given by this. So, nu is equal to 1 by 2p m square plus minus m. Okay. That is the filling fraction, and this filling fraction can be expressed in terms of a continued fraction, but importantly it needs to be noted that there is a term which is this, which is in addition to the m term that is there in the denominator. So, the Laughlin state only had this m term because Laughlin states only remained in the ground state. So, it is a ground state wave function. So, the hierarchy, so the continued fraction, or rather nu can be written in terms of the continued fraction as, okay. So, nu is equal to 1 divided by, so this is for for different values of p and different values of m, okay, odd integer m and different values of p. So, this is equal to 1 plus m plus minus 1 divided by 2 p1 plus minus 1 divided by 2 p2 plus minus and so on and so forth. Okay. So, this is the continued fraction that we talked about, and so this is like a p is having all these values 1, 2, 3 etc., and m has values 3, 5, 7 etc., and then one can actually form these continued fraction. So, let me show you one example of this continued fraction. So, let us just write for all the p's, let us call it a pj to be equal to 1, just to have a simple form. So, and m let us say equal to 3, that is also simple. So, at the third level, one has so nu becomes equal to 1 divided by 3 plus minus 1 divided by 2 plus minus 1 divided by 2 plus minus and so on. Okay. So, at the third level for corresponding to this thing. Okay. And I mean till the third level, then you can just drop everything out here and then calculate what fraction is coming out from this continued fraction. So, let me show you the picture for m equal to 3 and this pj equal to 1. So, the picture is like this. So, we have this. So, at the third level, so this there is 1. So, this the parent state is equal to 1 over 3. Okay. So, m equal to 1 over 3, and there are two branches that come out from the plus and the minus sign. So, let us write the plus branch here on the left and the minus branch on the right. So, at the P1 level, so this is Pj equal to 1. So, P1 level all the Pj's equal to 1, but you can have other fractions where P1 equal to 1 and P2 equal to say 2 and so on and so forth. Okay. So, this is equal to 7 by 2 that comes out from the positive branch. Okay. That is like 1 over 3 and plus, so this is how it is coming is that 1 over 3 and then you have a plus and a minus and 1 over 2. Okay. So, this becomes equal to, so there are 1 by 3 plus 1 half, that is giving you the 7 by 2 branch, and then so that is the plus branch, and the minus branch is coming out as 3 minus half, and that branch gives you 5 by 2. So, these are the fractions that are there, and let me go to another level. So, this plus branch here that gives you 5 over 17, and of course, there is a 5 over 13 from the minus branch. Now, this one will have a plus branch and the minus branch as well, and this is coming out as 11 by 3, do it carefully, and 7 by 3 coming from the plus branch and the minus branch. So, at the third level, so starting from one Laughlin fraction, we get so many non-Laughlin fractions coming out of this the hierarchy picture. Okay, and it gives you, of course, a large number of fractions. Not all of them are seen, and at the same level, it sort of even though it predicts that the probability of getting this fraction should be same, but that does not happen. Okay, I wish to close the discussion of this course here. So if you wish me to go back and talk about what has been done so far, and so we have started with mesoscopic systems. So this two-dimensional electron gas is a mesoscopic system, and then we have talked about Landauer formula. Then we have talked about in the related context, we have talked about S matrix, and we have talked about the discovery of the Hall effect, the classical Hall effect as well as the quantum Hall effect, and how Hall effect has a very important thing as metrology in determining the unit of the resistance. Okay. And of course, we have talked about classical Hall effect and this trajectory of the charged particles, etc., and so on. So these are all part of these classical Hall effect. Then we came to this quantum Hall effect. It's of course discovery, Landau levels, filling fraction. And when I say QHE, I really mean the integer quantum Hall effect, filling fractions, etc. Inclusion of spin, electric field, magnetic field into the problem, that is Zeeman, electric and magnetic fields. And we have talked about the incompressibility of the quantum Hall fluid. This is a very important thing. In fact, these plateaus actually at the plateaus, this mu doesn't even if you change the number of particles, it mu remains constant and so on. And then of course, we have talked about the chiral properties of this QHE. So these are chiral edge modes, edge states and so on. We have talked about SDH oscillation, which is an oscillation of the magnetization and so on in presence of the magnetic field. And then we have talked about so SDH oscillations, Kubo formula. Then we had gone to this QHE in a crystal lattice. So first we have talked about square lattice, and it's quite important to understand. So all these things are in 2D electron gas, and then first we have talked about square lattice, and we have learned how Piles coupling sort of modifies the hopping term there in the across the from one site, one lattice site to another. Then we have talked about the the topological invariant, which is the Chern number in this particular case. And then very importantly, we have talked about graphene in reasonable amount of details, what happens to the Landau levels in graphene and how they are different from the 2D electron gas, and what's the quantization like for the Hall plateaus in graphene, and they're significantly different than that of the 2D electron gas. We have also done Hofstadter butterfly. These are fractal structures that shown by the energy as a function of the field. And then we have talked about, importantly, we have talked about spin Hall effect, and so graphene is thought to be a candidate, however, because of extremely small Rashba spin orbit coupling, that is quite difficult to observe. So this is a non-dissipative spin transport. And its applications to spintronics. This has been touched in brief. And finally, we have done fractional quantum Hall effect. And there we have started with the symmetric gauge. Now this is by no means complete, particularly this part of fractional quantum Hall effect, because of the lack of time. I had to skip many important things such as the fractional statistics, the braid statistics, and then the many of these other things such as the topological quantum computation, etc. Those are definitely very interesting, however quite advanced topic as well. So this is symmetric gauge we have done. Then we have, of course, here I think we should also say that we have done the BHZ model in the context of a quantum spin Hall insulator. The symmetric gauge we have done, and then we have done the Landau levels. Then we have done the Laughlin states. Properties, plasma, analogy with plasma, rather plasma analogy, composite fermions, and the hierarchy picture. So with this I end the course. Hope you have enjoyed as much as I did. Some of these are slightly advanced topics, and you need to supplement it with a literature. A number of literature they have been cited along with, but there are more. Now finding out a relevant literature is not a problem with this internet being so fast and so resourceful. I hope that you learn more going beyond the course and take this course as a sort of the first level course in understanding the quantum Hall effect. Of course, there are other things such as anomalous quantum Hall effect, etc. we did not do in this course, which will be done in another course related to topology and condensed matter physics.